This book is Advanced Engineering Mathematics, 5th edition by Dennis G. Jill, Warren S. Wright. In this book, Part 1, Chapter 6, Section 6.3, Multi-Step Method. In this episode, we will implement Adams-Bashforth-Moulton method. Basically, we will implement this part of the book. Please pay attention to the title of each part. Part 1, Ordinary Differential Equation. Part 2, Vector Matrix, Vector Calculus. Part 3, Systems of Differential Equations. Part 4, Partial Differential Equations. Part 5, Complex Analysis. Once again, Part 1 is Ordinary Differential Equations. Then we skip Part 2. Part 3 is Systems of Differential Equations. Part 4, Partial Differential Equations. So, Part 1, Part 3, Part 4 deals with differential equations, y, vector, matrix, and vector calculus in Part 2. In Part 2, Chapter 8, we have to pay attention to diagonalization. Here, diagonalization is explained. Matrix diagonalization is very important. Diagonalizing a matrix. When a matrix is given, from this matrix, we evaluate eigenvalues or eigenvalues. Then using these eigenvalues, we create eigenvectors like this. Using these eigenvectors, we form a new matrix called P. So 3, 2, 3, 2, 1 eigenvector, 1, 1, 1, 1, K1, K2. These are called eigenvectors. Using these eigenvectors, we form matrix P. From matrix P, we evaluate inverse matrix. Using P and inverse matrix, we diagonalize original matrix A into diagonal matrix. So 1, 4. This is diagonal matrix. This is called diagonalization. This diagonalization plays very important role in solving system of differential equations. If we want to solve system of differential equations, we have to learn matrix diagonalization. Hi everyone, my name is Thomas Kim. Today is August 27th, 2022. This is my 47th episode for C++ 17 2023 CUDA SQL OpenGL OpenCL DBB. This is second episode about C++ differential equations. We will implement Adams-Bashforth-Moulton algorithm. If you want to follow my current episode, I assume you have watched my previous episode, episode 46, C++ Differential Equation 1. Please double-click this link. From our previous episode, episode 46, we implemented fourth-order Runge-Kutta algorithm. Using this algorithm, we will complete Adams-Bashforth-Moulton algorithm. Click Show More. From episode 46 source code, please double-click this link. Show in folder, unzip it, rename 47. Copy, paste it in your working directory. paste it here. Now open up your Visual Studio Code. Open CPP 17, 20, 23 parallel. From chapter 47, double-click Runge.cpp. Ctrl V. I will copy and paste these links. If you haven't watched my previous video, episode 46, please watch it. Otherwise, you may not be able to follow my current session. We implemented these algorithms in our previous episode. From Advanced Engineering Mathematics, Chapter 6, Section 6.3, Multi-Step Method. In this episode, we will implement this algorithm. I will arrange like this. Now, Ctrl End. Void test ABM method. So, ABM stands for Adams-Bashforth-Moulton. Auto F, auto X, auto Y, semicolon. We are solving this differential equation. Return x plus y minus 1.0. I would recommend SED floating point constraint. Also SED floating point constraint. This value is y4. So, auto y4 we call ABM method. We haven't made this function yet. We pass y prime this function, then initial value x is 0, so 0.0, then this value here, then h, the value 0.2 for h, then 1.0, this is y0, 1.0 is y0. SED, cout, ABM, y4, y4, SED, enter. Now we make this function here. Auto ABM method. We are implementing this algorithm. The first comes y prime f. So auto forwarding reference f. SED floating point. Auto x. SED floating point. Auto x upper. SED floating point. Auto h. SED floating point. Auto y. So this is f. This is x0. This is this x 0, 8. This is h. This is y0, initial value. Now here we compute xn, yn. I will make it bigger. Or xy tuples. In our previous episode, we created this function. We pass f x upper h y. Please understand that we implemented this function in our previous episode. std cout, we can display xy tuples, xy tuples, std enter. Now using y4t tag type y, std vector y, I would say yt, d y, dy reserve xy tuples size. We reserve memory for all xy tuples dy in place back. We are inserting up xy std cout dy std enter. Now all x3 y3 xy tuples back. Up to this point, we computed x prime, yn prime, yn minus prime, yn2 prime, yn3 prime. These are dy's. Okay, we call f, then set these values through this line of code. Then we have to evaluate this value. So copy, paste, or y4 star. This y4 star represent this expression. So y3, this y3 represent yn. So y4. If n is 3, then this is 4. So y4 star h over 24 0 times. We are evaluating this part. 55.0 times dy 3. We just evaluated this part. This part corresponds to this part. Then minus 59.0 times dy 2. So this term represents this term. 37.0 times dy 1. This term represents this term. Minus 9.0 times dy 0. Up to this point, we calculated this term y4 star. Then over x4 x3 plus h. Then dy in place, back up x4 y4 star. This represents y4 prime. This represents this term. Then we evaluate this part. Return yn is y3. y3 plus h over 24 times. I will line break here. 9.0 times dy4 plus this term corresponds to this term. Then 19.0 times dy3. Then this term. Minus 5.0 times dy2. Then this term plus dy1 semicolon. Now this function is completed. If it has error, then it will spit error. Now we will open Microsoft compiler. cd 047 Runge-Kutta clehsc sdd c++20 runge.cpp fem.exe, hit enter. Sorry, I made mistake. It should be lowercase c. Okay. Sorry, we haven't called this function. Copy. Paste it here. disable it, we rebuild. CLS M. The value 1.42553. Then we compare with the result. In the next page, you can find y for this value. So y4 is this value is this value, 1.42553, 1.42554. This is exact value. This is our computational result, 1.42553, 1.42557. So our computation and the computation in this book almost matches, and this is the exact value of y over 0.8. So our solution is correct. If you compare these values, for example, here we initially compute y1, this value is this value, 1.0214, 1.0214, y2, 1.0918, 1.0918. This value is this value, 1.22211, 1.2221. This value is this value. Here xy tuple, Control B. In this computation, xy tuples, this value represent these values, y1, y2, y3. y1, y2, y3 represent yn, yn minus 1, yn minus 2, yn minus 3. These numbers are this number, this number, this number. xn, xn minus 1, xn minus 2, xn minus 3. These numbers are 0, 0.2, 0.4, 0.6. So we compute xn, yn, xn minus 1, yn through xy tuples, Then using these numbers, we compute yn prime, yn minus 1 prime, yn minus 2 prime. These are computed using this loop. We are calling fxy. We are calling this function, then compute yn prime, y minus 1 prime. These are dy. Then using these numbers, we extract the last value over xy. Using this, we compute y star, yn plus 1 star. So we compute this expression. Then using this y star, we compute this expression. This expression amounts to this part. Then Using these values, we compute this expression here. So this function returns this value. This value is y4. I will put another message. In our previous episode, we created solve RK4 method. We can call like this: RK4 Y4. I will paste once again. Then we can call like this. Then I will std and there. We build once again. 176. Sorry, I made a mistake. We have to return Oro. I fixed. We build again. CLSM. So we evaluate the Y4 using RK4, this function. We implemented this function in our previous episode. RK4 is very famous function, fourth order Runge-Kutta method, so matches with our result. I understand this is quite complex. Also, this book does not explain. This book does not explain much about these things. But in this book, Advanced Engineering, Peter V. O'Neill, this is 6th edition. In this book, Chapter 5, Numerical Approximation Solution, Section 3, Multi-Step Method. In this book, Section 5.2, you can find the explanation. For example, case 4, R4. This expression is this expression. This expression is this expression. This expression is this expression. So, if you cannot find your answer from this book, refer to this book. That is what I call cross-reference.